So this term half-life is a very important term when it comes to radiation, okay? And different isotopes have different half-lives. So for instance, something like carbon-14 has a half-life of about 5,700 years. Something like uranium-238 will have a half-life of 4.5 billion years. So there can be vast differences between them. So something like radon gas, it's about 3.5 days. You get others that'll be measured in milliseconds. Even things, other isotopes of the same element, so something like carbon-13 has a very different half-life to carbon-14. But for each individual isotope, the half-life is constant. It's something that we can't change. It's not like a chemical property. Like if you're having a chemical reaction, we can speed that up by increasing the surface area, by raising the temperature. Doing those things with our isotopes does not change the half-life. Okay. Now we define half-life one of two ways. It is either the time taken for the number of unstable nuclei in a substance to decay to half that amount. So for instance, let's say I did have carbon-14 and I have, let's just make it 16 unstable carbon-14 nuclei. It'd be the time taken until half of them remain. Now that doesn't mean that the other half go missing. The other half, in fact, would change into nitrogen. We don't know what ones are going to do it, but it'll be the time taken until there's just 8 remaining. So we would have 16 at the start, and it's the time taken for that to get down to 8. Okay. Counting individual nuclei is difficult. We can do it if we can measure the mass of them, but even that sometimes can be hard. So instead, what we quite often do is we just get a Geiger-Müller tube, connect it up to a little count meter, account for background radiation and everything else, and we just measure the activity from the source. Okay, so maybe the activity at the start, we might get, say, I don't know, 200 counts per minute. Okay, that's the amount of disintegrations, decays we get in a minute. There is another unit for activity, which is becquerels, which is just number of counts per second. We'll tend to stick with this one maybe for this example. So let's say this gives 200 becquerels. We want to find out how long it takes then until the activity measured drops to 100 becquerels. Quite straightforward. So our two definitions, and they are definitions that I would learn off, is the time taken for either the number of unstable, and that word unstable is important, nuclei in a substance to decay to half the amount, or it's the time taken for the activity from that source to drop to half that amount. The next video we'll look at the maths behind this without graphs, but just leading on from your Skittles experiment, here's an example. It says calculate the half-life of the source in the following graph. So what we do is, it starts off with 80. It's the time taken for that to get to half its value, and if we look closely at this graph, you should see that's about there. So what I would do is I would draw a little line across and a line down, and you should see, and this is a symbol we use for half-life, capital T with a little subscript of half, it's 2 seconds. But we can do better than that, because we want a reliable value from a graph. So this value should be constant. So the time taken to get from 80 counts per minute down to 40 should be the same amount of time to get from 40 down to 20. And we can just see that because if I measure across there, then the time taken to get from 40 down to 20 is also 2 seconds. I would always look for two values. So I've gone from 80 down to 40 and then from 40 down to 20. But there's no reason why I couldn't have done this. If I choose a different color, I could have took my second value to be 60 and seen how long that took to get down to half that, 30. And it should be about 2 seconds again. Once I've got two readings, what I then work out is an average. So from 80 down to 40 was 2 seconds, from 40 down to 20 was 2 seconds, and I just take an average of those two numbers, so I divide that by 2. Gives me 2 seconds, obviously. However, there is usually a mark for this step in exams, so you show it. Even if both the times you've got are the same, you show that you've taken an average of those readings.